Hello. So here I will be demonstrating some asynchronous and synchronous counters. So I'm going to go ahead and start off with asynchronous. As we can see, I have a multitude of circuits up here. I'm going to go ahead and start off with the 4-bit count up and down counters. So over here I have the count up, so this is going to count from 0 to 15. I'm going to go ahead and just connect the clock and go ahead and just demonstrate as such. So since everything is negative edge triggered, I need to go ahead and just trigger the clock, and from there just run the I apologize. I will go ahead and trigger the reset switch because it's negative edge triggered, and then I will go up here to the clock right here and go ahead and run it, and this will count from 0 to 15. Anytime I want to reset the numbers, I'll just go ahead and turn it off and then back on high. So here you go. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And then it's going to go back to 0. Just hit reset, and I'm going to go ahead and just disconnect the clock so it's not running later on. Because, as we know, anytime you hit this clock button, it's universal. Any other clocks you have here in Logisim are going to run. I'm going to just demonstrate the countdown. This is the opposite of the count up. It's going to count from 15 to 0. And same, because it is negative edge triggered, I'm going to go ahead and just trigger the reset button, the clear, and then run the clock. So it's going to go from 15, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And it starts over. I'll just go ahead and reset that and disconnect the clock. And next up, I do have a decade counter down here. I do find myself confused on how to actually test this counter, but it is supposed to count from 0 to 9, then recycles. So here it is in its full glory, so we can see all the flip-flops, negative edge triggered, as you can see by the NOT gates everywhere. So running the clock pulse will really only trigger the first flip-flop, and it goes from least significance to most when it comes to outputs. So, like I said, I am a bit confused on how to actually implement and test this circuit. I have 3 there. Even I can see that. So I'm just here playing with the circuit. Just going to reset that, disconnect the clock. Yes, this whole circuit was really just to count from 0 to 9. Over here I have a divide by 6 circuit. So this is going to count from 0 to 5, and it requires 6 clock cycles right here. And here I have a divide by 6 asynchronous counter. So with this here, everything is negative edge triggered, of course. So to actually be able to run the circuit, I'll need to have the clear switch on high, run the clock. Over here with these other inputs, A1, A2, it counts in a sense as another clear switch. It will force whatever outputs I have to be set to 0 if I have both on. This is 6 in binary, of course. But this whole whole point of this is just count from 0 to 5. It won't actually reach 6 because, as we know, in digital design, 1 actually starts at 0. So 0 through 5, you can count that as it cycling through 6 numbers in actuality. With the circuits, it'll actually output 6, but then it'll reset back to 0. As you can see, does work properly. There is a glitch though. In my circuit, it goes to 7 before restarting. But the whole point of a divide by 6 circuit is to go up to 5. Quick glimpse of 6, and then back to 0. And down here I have my synchronous counters. I'll go ahead and just demonstrate my 4-bit synchronous counter. So with synchronous counters, the clock will connect directly to each and every clock input rather than an asynchronous counter in which you'll only have the one clock connecting to the first flip-flop, and from there it all cascades down into the following flip-flops. Here everything is direct. And as before, these are all negative edge triggered. So I also have this enable switch here. I'll need to trigger that as well as a clear switch to go ahead and be able to actually cycle through this synchronous counter. So it starts from 0, goes to 15. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and we are back at 0. So here I have the synchronous decade counter. Like the synchronous counter before, I have the clock switch that is directly sent into the clock input of each flip-flop rather than it being sent to one flip-flop and cascading down into the next. So this decade counter here is going to count from binary 0 to 9, and then recycles, aka starts all over again. So I'm just going to go ahead and start. I need to hit the clear switch because everything is negative edge triggered. So let me go and get started. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then back to 0. Hit the clear switch just to reset it. Disconnect the clock. And in here I have a specialized synchronous binary counter. So as you can see, there are no direct outputs like we have in the other circuits we have created. It's all just going to be really shown in each flip-flop. So I'm going to go ahead and simply just start running it. It is not negative edge triggered unlike the other circuits we were looking at, so clear switch is as per usual, and yet I could keep it off. And you really just see the outputs in the flip-flops themselves. I will be looking at a table as I run through this. So when I get started, first we're going to start off with, it's going to go from, this is least significant to most. So we're going to start with 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 100, and finally at 0. And it starts over again, a little pattern, just to clear.